we talking about? So again, I'm going to go with example 1 from your book, okay? Because they do something here that's nice in that you can put your hands on it. You can see what we're doing here. So in this problem, the constraint, it's kind of like the last problem that they did. Example 1 of the last section, they had that plane. And they said, hey, pick any point, x, y, and then you automatically define a rectangle, right? And we're trying to maximize volume. In this problem, again, we're going to pick x, y. Any point you want in the first quadrant. And when you do, well, I guess there's some things you can't pick. We want to pick a point, and once I get that point, let's say that I have to be within the ellipse x squared over 3 squared plus y squared over 4 squared is 1. Okay? So that's the equation of my ellipse, and they graphed it here in black. And this is what we're going to call our constraint. Okay? That's the constraint. I have to be on the ellipse. And what I'm trying to do is maximize the volume of the red rectangle that I get. Okay? Area, yes, area. Maximize the area. So what is the area of the red rectangle? Well, just this little piece of it is xy, right? So the objective function, as it's called when you take other courses, okay? This is the function we hope to maximize or minimize. Function we hope to optimize. Yeah. So for example, in the other problem, my objective function was s equals, and I gave it to you indirectly. I said, well, it's surface area. Then you said, well, okay, it's xy plus 2yz plus 2xz. Yeah. So how could they have worded this problem? They could say, okay, find the maximum area of a rectangle that can be inscribed in this ellipse. That'd be a nice, clean way to word it. And this is what you're trying to find, right? We have an objective function, and we have an ellipse. Now, the trick that we're doing, I should have written that here maybe, trick. Think of these equations as equations of level curves, right? How many dimensions am I in this problem? 2, right? In both cases, two-dimensional problem, but although I guess the objective function is really a function, it's a function of 2 variables, so the graph is in 3 variables. So what you want to do is think of these as equations of level curves. Look at it this way. I have x squared over 3 squared plus y squared, why don't they write 9? 9, 16 equals something, right? In this case, it equals 1. But I can think of it as a level curve of the something. You guys with me on that? And similarly, I can think about level curves here. I could put in various values of z equals f of x, y. And when I do that, I get level curves. Okay? So the picture on the next page kind of shows you the idea. See, they say, let's take that function f of x, y, and let's set it equal to k. And for various values of k, well, the nice thing is that each one of these graphs is a hyperbola. You guys all know that? Because you have y equals whatever k is over 4x, right? It's basically like the curve 1 over x times something else, right? So they're all hyperbola. And if you graphed each one of them, as k got lower and lower, you'd be moving closer and closer to the ellipse, right? Now since xy has to be on the ellipse, you want to intersect it at some point, right? And if you're trying to maximize 4xy, what you want, oh, that's a bad level curve. What you want is you want the level curve that is just tangent to it, right? And if you did that, that would be the right xy. You guys follow it? So there's the geometric idea. Now let's try and say it algebraically. How do I do that? How do I get these level curves to be tangent to the ellipse, which I'm thinking of as a level curve? Equal to what? Okay, so you're now doing this problem like we did the last one, right? Where we got rid of a variable, right? And you could. But here's another approach. And it has to do with the idea of thinking of level curves. Do you guys know anything in this chapter that we studied that has something to do with level curves? Gradients. What do we learn about the gradient and the level curves? The gradient is orthogonal to level curves, right? Yeah, that's exactly right. So what I'm going to do is I'm going to look at gradient of f. These level curves here? Well, they're all 4xy is a constant. So when you go ahead and take the gradient, the constant you don't have to worry about, right? The gradient's going to be the same. And I'm also going to take a look at gradient of g, right? And if these are tangent level curves, that means they touch only at one point. But remember what the gradients are. Gradients are vectors in the xy plane. And which way do they point? Well, like you said, they have to be perpendicular to the curve. And so if these are tangent, well, what has to be true is that the two gradient vectors have to be what? In the same direction, yeah. I mean, maybe I drew it bad, but they both have to be pointing the same direction. I guess they could point opposite directions. And what's that going to look like when you write down an equation? Well, what you're going to get is this nice equation, right? Gradient of f is going to be some scalar times the gradient of g. Right? If you're a scalar if one vector is a scalar multiple of another vector, then they're parallel. Right? Okay. So this is the nice Lagrange equation. Gradient equals lambda times gradient. And the idea is we added a variable. Right here. We're going to add the variable lambda. And then we will get the situation we want. So here's the theorem. Can you always do this? No. You need the following. You need f and g to have continuous first partial derivatives. Of course, most of the functions we've had, that's true. Okay, we'll call it a nice function then. So if f and g have continuous first partial derivatives such that f has an extreme and a point x naught, y naught. So let me say this in English. If f has an extremum, then we're going to have, well, this equation. The gradient of f evaluated at x naught, y naught, I should say at x naught, y naught. The gradient of f evaluated at that point has to be lambda times the gradient of g evaluated at that point. See, in the picture on the previous page, whatever point this is right here, that's my x naught, y naught. Okay. Go ahead.
Just kind of like getting into that proof like that.
Which proof?
Remember when we were supposed to prove that the gradient was normal to a level surface? And it had to do with this like strongly.
Yeah, well that's just one dimension higher, but it's the same thing. Yeah, and we did prove in class, I think, that it was normal to a level curve. But yes. Who else had a question? Jonathan. Let's do it. Let's do it. I'd love to. We wish to build a rectangular box with an open top that has volume V. What should be the dimensions of the box if we wish to minimize surface area? Okay. So, here's the game. Let's see. Our objective function is S equals, well, let's call this f of x, y, z. Okay? That's going to be what I call f. And so it's xy plus 2xz plus 2yz. G is the function that you typically use for your constraint. Yeah, so what was my constraint? Well, the constraint was the volume. So what was the equation? X, Y, Z has to be V, right? Well, when you go ahead to do these problems, what you want to do is you want to make sure that your constraint is set equal to 0. I think it even says that in the theorem. Let me just look at that. No, they say G equals a constant. All right, well, that's fine. So I'm going to say G of x, y, z, I'm going to make it equal to x, y, z minus v. Okay. I guess I didn't have to subtract the v, but it's my habit here. Okay, we wish to minimize the function No, gxyz is not equal to v. It's the constraint. So I guess the constraint, v is a constant, right? So our constraint, once we have that constant, our constraint is going to be that xyz minus v has to be 0. How's that sound? Okay? Okay, so get rid of this piece, but that's the constraint then. Your constraint is going to be g of your stuff equals 0. And notice, I'm already kind of jumping the gun here because the theorem that we stated is for functions of 2 variables. But the problem that we're doing, because I'm not going to substitute, it's actually for functions of 3 variables, isn't it? Now what we did when we did the problem the first time was we had x, y, and z, but we solved for z and we just dealt with functions of x and y. Right? Here you're actually going to add an extra variable. It's kind of weird. So we form the function, which I'm going to call big F, because that's what we've been doing when we form these functions. So big F is going to be a function of x, y, z, and lambda. And I'll just say we form this function. Now what is this? This is f of x, y, z plus lambda times g of x, y, z. What am I doing? Here, let's go back to the theorem. It says that the gradient of f has to equal the lambda times the gradient of g. All right, we'll come back to that now. Here's what I'm forming, big F. So this equals, let's see, xy plus 2xz plus 2yz plus lambda times x, y, z minus v. what I'm going to do now is I'm going to find the critical points of big F. Okay, critical points of big F. So let's look again. We're going to use the theorem that gradient of F equals lambda times the gradient of G. Okay, and really this is a vector equation. Okay, so this vector equation yields a number of scalar equations. Okay, so what do I get? Well, gradient of F. So basically what you can do is you can go through component by component, right? So we have the partial with respect to x, right? That's going to give me an equation. It's going to give me y plus 2z equals, what else? Lambda times, and I guess it would be yz, right? Because that's the gradient of g. That's the partial with respect to x. Now you can write down similar things for ddy and ddz. Okay. So ddy, let's see, I get x plus 2z is lambda times xz. I get z, no, what do I get? 2x plus 2y, right? 2x plus 2y equals what? Am I going too fast? I'm going way too fast. Let me slow down. Question was, what's lambda times yz? It's going to be lambda times the gradient of this guy, right? Well, the gradient of this guy, if I'm just talking about the first component, ddx,
It's just yz.
yeah, it's just yz. So that's why here I'm going to get lambda xy, because I'm taking the z partial, right? So, yeah, these are vector equations, but you're really getting 1, 2, 3 scalar equations, one from each component. You guys with me on that? Now here's what they don't tell you in our book, which is where I was throwing big F in the mix, and I guess since they don't, I'm going to stay away. I'll still tell you, but they're going to write down now as one extra equation, okay? Well, xyz minus v has to equal 0. Okay? But I guess what I'm going to tell you is, you would get that if you did the big F trick, where you're going to take little f minus lambda g. You would get that from partial with respect to lambda. Because where's lambda? Well, lambda's just this guy right here. See that? So you would just get basically g. Okay. Is this okay? And for certain generalizations, you need to think about it that way. Now, really what you're doing is you're upping a dimension and taking all the partials so that you're finding the critical points of this new function. That's really what you're doing. But anyways, you now have how many equations? 4 equations, and how many unknowns? 4. So we ought to be able to solve it. Well, in theory, right? So the question is this easier or harder than what we just did? And the answer might be easier, actually. Okay. What? Yeah, do you see it? Well, you could solve for lambda. What does lambda equal? let's do this. Let's take these first two equations. Let's mess with those for a little bit. So what do I do? We can definitely get rid of the two z's here, but just by subtracting, right? So if I subtract, I get, let's see, y minus x, okay, plus, you can factor out the lambda, and you can factor out the z, and then you get y minus x, right? So that's kind of nice, because now I see a common factor. Do you see it? Y minus x, and this equals 0. So y minus x times what? 1 plus lambda z has to be 0. So what does that say? Either y equals x, right, if that's 0, or, well, let's see. How about I do this? Lambda equals negative 1 over z. There's my nice or. Here I use the fact that z does not equal 0. Right? I'm not going to take z equals 0. That'd be a bad move. So this is interesting. Already I learned that x and y should be equal. Remember that? That was one of the facts that we learned. Now, you know, one question you might have is, what the heck is lambda? And the answer usually is, who cares? You just kind of threw in a variable. Okay? It's not always who cares. Your book talks about a nice application in economics where people figured out what lambda means. And there are applications like that, but that's kind of weird. Okay, so let's see. Substituting this, once we know that lambda is negative 1 over z, we could go back to the second equation, let's say. Okay. I'm going to take this guy, throw it in there. Okay. So what does that give me now? I'll write it down here. I get x plus 2z equals what? Isn't it negative x? Right? So negative 2x. I did something wrong here. Lambda is negative 1 over c. So x plus 2z equals negative x. Ooh, I see what I did wrong. Scratch that, because, yeah, the lambda stuff was on the other side. So this is equals. Y minus x equals lambda z times y minus x. So this is minus right here. So this is plus. When you do set it equal to 0, it becomes a minus. So this is lambda is positive 1 over z. Sorry about that. And now, when I plug in, lambda is positive 1 over z. I get x plus 2z. That's not right either. Equals x. I guess so. But then you get z equals 0. And if you get z equals 0, we're not very happy, right? So I guess what we learned from this is we really don't want to go to this solution. Yeah. That's the minimum when z equals 0. Go ahead. This whole thing. I subtracted these equations. Since you subtracted equations? Okay. When you solve systems of equations, there's basically two tricks you could do that I know of that you learn in algebra class. You either do a substitution, which means you get one variable by itself, substitute in for the other one, or you can add or subtract them. Or first you multiply by something and then add or subtract them. And that's about all you can do. And I will say that these systems of equations that you're going to get when you do Lagrange multipliers are going to involve some very creative algebra solving. Okay? It's one of the downsides of doing this. But sometimes it actually does make the problem easier. Okay? I mean, what would you try? I don't know. Anyways, I guess what we learned so far is that you don't want the circled possibility. Okay, let me get a different pen out for what we do want. What do we want? We want to use y equals x. Okay? You guys with me on that? So if we want to use y equals x, let's see. Let's throw that into an equation. Let's see. Let's throw it into the third equation. We haven't used that one yet. So let's see what it gives me. It gives me 2x plus, well now I could just say 2x, right? Equals lambda x squared. Okay. So 4x minus lambda x squared equals 0. And again, I'm going to factor, and I get 4 minus lambda x times x is 0. You don't want x to equal 0. So it looks to me like x has to equal 4 over lambda. Okay? Now, remember that x equals y. So y also has to equal 4 over lambda. And we want to get what z is. So let's see, how am I going to finish up? Well, now I'll go back to that equation up here again that relates them, right? So let's see. Finish over here. Let's see what I know. Well, I know x is 4 over lambda. Plus 2z, I don't know z yet, I'm trying to figure that out, equals, well, you get lambda times 4 over lambda times z. That's just 4z, right? So I get 4 over lambda equals 2z. So z is 2 over lambda. Ah. Now, does that solve the problem? We've got x, y, and z all in terms of lambda. I guess we don't know what lambda is. What would you have to do if you wanted to get lambda? There's something we haven't used yet. I just solved for z. No? Let me go through what we used. Yeah, we didn't use the constraint. Right? We did all this work, lots of algebra, but we haven't yet used the constraint. Okay? So I guess to finish, what would you do? You'd say 4 over lambda times 4 over lambda times 2 over lambda has to equal v. And so you get lambda cubed times v equals 4, 16, 32. So lambda is the cube root of, well, 32 over v, which I think would simplify the exact same thing you got before. Well, at least that's lambda, and then you could get z, x, and y from that. But I guess the point is, remember what we really cared about was what shape box do you have? And notice that we already know that the x and y are twice as big as the z, even without knowing anything about lambda. Okay? Now, this kind of displays a little bit of the nasty algebra that can happen using this method. But it's also very beautiful and powerful. There are problems that you can solve this way much easier than other ways. Okay, last example. Here we go. Find the highest point the curve, that is the intersection of the cone z squared equals x squared plus y squared, and the plane x plus 2y plus 3z equals 3. And I realize there's 9 minutes, but if we spend 1 minute of it imagining the geometry of this problem, I think that's worthwhile spending. Draw a little picture to convince yourself of what you're trying to find. Well, this is a cone through 0, 0, 0. And what do the level curves of this cone look like? They're circles. At any particular z value, I have a circle, right? So that's the picture of the cone. And then I'm intersecting it with a plane. Oh yeah, it's a conic section, huh? So what's the curve that we're talking about? What shape is it? Well, I don't know. It's a conic section. It could be an ellipse. I would guess that's probably what it is, right? So we're trying to find the highest point on the ellipse, and according to my picture, it's right there. Okay? But there's nothing to say my picture is right. Okay? I mean, does the plane really look like that? I don't know. But I'm trying to find that point. You guys with me? Now, could you do this using the techniques without Lagrange? Yes, you could. What would you be trying to maximize? Maximize what function? Z. I mean, you could think of it as a function of a couple of variables, but we're trying to maximize Z. Now, could we write this curve using an equation? Well, maybe. What would you have to do? You'd have to solve the system involving this equation and that equation, right? So I guess you could isolate x, and then everywhere it says x, you could put in y's and z's. But it's starting to get to be messy algebra without doing anything yet, right? We haven't done any calculus yet. Lagrange multipliers can help in this situation. To do this, though, you need to turn to the very last example on page 973. So page 973 shows what to do if you have more than one constraint. So if you have more than one constraint, so they use G and H here, I guess that's fine. What you do is you get gradient of F equals lambda times gradient of G plus, and then they use this Greek letter, mu, times gradient of H, where both of these are constraints. As many variables as you want. So the way I usually see it written, it's lambda 1, lambda 2, up to lambda n, and it's G1, G2, up to Gn. Okay? So yeah, you could do this as much as you want. And that's really nice, because now solving this problem isn't really any harder than the one we just did, other than maybe the equations aren't so nice. But we'll see what happens. So let's see. These are my constraints. So I'm going to call this guy G of x, y, z. And he has to be set equal to a constant, so I'm going to call him x squared plus y squared minus z squared. Okay? The other one, I guess, is fine, but I'm going to do it anyways, just out of habit. H of x, y, z is, let's see, x plus 2y plus 3z minus 3. Okay. Just my habit of doing that. Oh, what's f? F of x, y, z is the objective function, and we said that is z. That's actually going to help a lot, because the equation I get, right, Lagrange tells me that the gradient of f is, well, I wrote it up there already, right? Lambda gradient g plus mu gradient of h. So, we're going to get different equations. First, when I do the partial with respect to x, well, what is df dx? That's just 0. So the equation I'm going to get is I'm going to get 0 equals, okay, so I need 2x is what gx is. And what's hx? Hx is just 1, right? So the first equation I'm going to get is 0 equals 2 lambda x plus mu. Did you guys get that? If you get that, I've probably done my job. I've probably done enough that you can solve it. May as well write down a few more. From the ddys, what do we get? 2 lambda y plus 2 mu, right? Oops. And then from the ddz, well, here's where I actually have a partial. That's non-zero. I get 1. I get 1. By the way, one restriction, you can't use Lagrange if the gradient of your function is 0. So luckily here, it was non-zero. Okay. So here we get 1 equals what? Negative 2 lambda z plus, yeah, 3 mu. Now, that's only 3 equations and how many variables? Actually, 5 now, because I added 2 Lagrange multipliers. Well, the other equations come from the constraints. So we also have 0 is x squared plus y squared plus z squared. Oh, let's see if I do this right. Hang on. Hang on a second. Yeah, it's minus z squared, but also I did something wrong. Let me think. No, that's right. And then the other one is 0 equals x plus 2y plus 3z minus 3. And in theory now we have enough. We ought to be able to do it. Okay? And now you get creative and have fun. That's why I think you'll like the homework for Thursday. Okay? I think. Yeah. And again, where's it come from? It really comes from making a big F of 5 variables and doing dd lambda and dd mu. And then this is the equations you would get from those two. That's really what you're doing, even though our book doesn't say that. Okay, out of time.